All right, so welcome to the solutions unit. To get started, we're going to first go over some terms that you'll need to know just to get settled into this unit. Okay, so essentially what we're doing is we're talking about all the different forms that matter can occur in. Okay, so what matter is anything that has both mass and volume. Okay, so if we're talking about table salt, which is just sodium chloride, because it has a mass and takes up volume, it is matter. Okay, oxygen gas has a mass, takes up volume, so it is matter. Okay. Now, matter can be divided into substances and mixtures. So a substance is just matter with a constant composition. So all the particles have the same properties. So what's going to make that up are either elements or compounds. Okay, if you have an element of something, then any substance that is that element is going to have the same atomic number, the same amount of protons, same amount of electrons, neutrons, so on and so forth. Okay, whereas if we talk about a compound, it's going to be a substance that's made from two or more elements which are chemically combined. So chemically combined meaning it's being held together by ionic bonds, covalent bonds, that sort of thing. Okay. Now with mixtures, that's where matter can have a variable composition, so it can change throughout the substance. Okay, and it's made from two or more substances. Okay, so if we think about soil, right, we have some of it's dirt, some of it's rocks, there's earthworms in soil, all of that good stuff. And sometimes, you know, if the soil's aerated well enough, there's going to be gases in there as well. Okay, now mixtures can either be homogeneous or heterogeneous. Okay, so homogeneous just means that it all looks the same. Okay, so for example, if you took a glass of water, threw in some salt into it, and stirred it up to make sure that all the salt's dissolved in the water, right, it would look like it's all the same thing, like everything in that glass of salt water is the same. You couldn't pick out the little individual pieces of salt compared to separating it from the water. Okay, not visually at least. Whereas heterogeneous mixtures, those are mixtures where you can look at it and see all the different parts. Okay, so if you're thinking about, let's say, a chocolate chip muffin, you can separate like what part is made up of like the dough versus the chocolate chip, right? And if you didn't mix your batter well enough and you have a clump of flour, you know, you can tell that that's separate from the rest of the batter and the chocolate chips as well. Okay. So like we said, a mixture is a physical blend of two or more substances. However, keep in mind that they are not chemically combined. Mixtures can either be homogeneous or heterogeneous. So if you look at a mixture, it can either look like it's all the same throughout the entire mixture, or you can see the different parts to it. Okay, so once again, heterogeneous just means that you can see all the different parts. Okay, so I talked about a chocolate chip muffin. Another example would be a chocolate chip cookie. Or if you're thinking of maybe banana bread that has walnuts in it, you can clearly tell, you know, the bread or the cake mixture from the banana bread versus the walnuts. You can see the different parts. Whereas homogeneous, it all looks the same. Okay, and if you have a homogeneous mixture, okay, that's also called a solution. Right, so some examples of solutions might be something like hot chocolate. If you like don't put any marshmallows in it, or Kool-Aid, or hot sauce, or even something like teriyaki sauce. All of those are solutions because you can't tell the different parts of each of those solutions I just listed. Okay, some more examples of homogeneous solutions, or homogeneous mixtures, I should say. So homogeneous mixtures and solutions are the same thing, just two different words. Oop. Okay, so you could have a solid-solid solution, so that means you have one solid kind of dissolved into a larger bit of solid. So something like stainless steel, if you take a look at it, you can't pick out all the parts. You can't like point at a specific part and be like, oh, that's where the iron is, that's where the carbon is, right? Same with sterling silver or chocolate. You can't tell all the different parts to it, but something like chocolate, it's made up of other solids like cocoa, sugar, butter, so on and so forth. There's solid liquid solutions, so something like coffee. So you can't tell the difference, or you can't visually separate out like the coffee from the water, or ocean water. You can't separate out the salt from the water, although ocean water is a little bit of an imperfect example, because if you think of the bits of seaweed, or just even if there's unfortunately trash in the ocean water, like obviously you can tell the difference between those two things, but for ocean water we're essentially just talking about salty water. Same with lemonade, can't tell the sugar from the water. Gas liquid solution, so for example pop, you can't really separate like the sugary syrup from the water. Okay, or for a water in an aquarium, separate out like the dissolved oxygen in the water. You can't visually tell that. Okay, so last but not least, we have a gas-gas solution. So if you take a look at the air around you, you can't pick out all the different types of gases that are in the air. So the air that we breathe, a lot of it is nitrogen. Obviously there's oxygen and carbon dioxide in it, as well as other gases such as argon. However, you can't pick out the different gases even just looking around you at the air. Okay, now solutions, you do need to be aware of the different parts to a solution. Okay, so what a solution is it is something that is formed by dissolving a solute in a solvent. Okay, so a solute, that's the thing you're going to have less of. Okay, and it's a substance that gets dissolved. Whereas a solvent is the substance you have more of, and it's going to do the dissolving. Okay, so a solute could be solid, liquid, or gas, and same with a solvent. It could be solid, liquid, or gas too. Okay, and one of the most commonly used solvents in day-to-day life, that's going to be water. Now, let's just write down what I said as some notes. Substance you have less of. Substance you have more of. So if we're talking about making a solution of Kool-Aid, right, you have like the Kool-Aid powder that you're going to put into the water. So the solute is going to be the Kool-Aid powder, and the solvent is going to be the water that you stir it into. And once it's all stirred up, then you've made a solution of Kool-Aid. Okay, So here's some more examples of different solutions. So these are all homogeneous mixtures. You can't tell the different parts of them. Okay. And this is just to prove, okay, your solute, so what you have less of, can be solid, liquid, or gas. And same with your solvent, could be solid, liquid, or gas. Most often when we think of solutions, though, we think of things dissolved in water. So talking about water as a solvent, okay, it's very common, and that's because it is a polar molecule. So when we're talking about polar molecules, if I draw a structural diagram of water here, so oxygen is more electronegative than hydrogen is. Let me put the lone pairs there. So if I was to do dipole arrows on this, okay, I would point them towards oxygen because the dipole arrows always point towards the more electronegative substance, or atom, I should say. So with this, we can see that the electrons in water, they're essentially skewed towards the part of the molecule, or the part of the compound, sorry, that is where oxygen's at. So this is what this resultant vector is trying to show, is that the electrons are more so up where oxygen is. So polar just means there is an unequal distribution of electrons in a compound. Okay, so when we're talking about water having a positive and a negative end, what we mean by this is the negative end is going to be where all the electrons are kind of skewed towards, because electrons have a negative charge to them. So I'm going to denote this with a little delta negative right here to represent what I just said, that the electrons are kind of skewed towards the side with oxygen. And because the electrons are leaning towards where the oxygen is within their bonds, that means where the hydrogens are going to be delta positive, or a slightly positive charge, because there's less electrons by the hydrogens. Okay, so that's what we're meaning when we say that water has a positive and a negative end. Okay, so water, it's polar, has a positive and a negative end. And because it has a positive and a negative end, the water molecule is going to orient itself so that the positive end of the water molecule is closest to a negative ion if you're dissolving an ionic compound. Okay, and that's just because opposite charges attract, and the negative end of water is going to be closest to a positive ion, once again, if you're dissolving something that's an ionic compound. Okay, so here we've got a picture of sodium chloride being dissolved in water. So even though it's a little bit grainy here, this gray ball right here, okay, that's going to be our sodium ion, so that's a cation, it's a positive ion. And the red balls here, those are going to be like the slightly negative sides of water, kind of grouping or getting close to the positive ion, or also known as a cation. Whereas if we're talking about the chloride ion, which is this kind of bluey green ball here, notice how like these parts right here of our water molecules, those are supposed to be representing like the hydrogens, which, as we said, that's going to be where we have a slightly positive charge to our water molecule, and they'll be attracted to the negative ion, the chloride ion, which is also called an anion. Okay. So because water molecules are very polar, they're attracted to other polar molecules as well as ions. So what this is saying is that water is going to help to dissolve other polar molecules, which we've talked about before with like dissolves like. So polar dissolves polar, non-polar is going to dissolve other non-polar substances. But that's what this is referring to. Water molecules, they're polar, so they're going to help to dissolve other polar molecules as well as ionic substances which are soluble in water. So when I say ionic compounds that are soluble in water, I just mean ionic compounds that are able to dissolve in water. Not all ionic compounds are going to be dissolvable in water. Okay, so water has a negative end and a positive end, which allows it to break apart most ionic compounds. So when ionic compounds break apart into their ions, that is called dissociation. So dissociation is a term that you're going to want to know about because it will be used in the future, and the key part that you know is when it's specifically ionic compounds breaking apart into its ions. That's what dissociation is. Eventually we'll get into something called ionization, which is talking about when molecular compounds break apart into their ions. Okay, but for now, dissociation, that's when ionic compounds break apart into its ions. Okay, and as we said before, some ionic compounds, they're not going to dissolve in water because the ionic bonds between the ion solute is too strong. Okay, now, if a salt crystal is put into water, the polar water molecules are going to be attracted to the ions on the crystal surface. Okay, and when those water molecules surround the ions, that's a process that's a part of dissolving called hydration. Okay, and when the ions break apart, that is called dissociation. So remember that this is specifically for ionic compounds. And the surrounding of the solute particles by a solvent is just called solvation. So what's the difference between solvation and hydration? Well, hydration just means your solvent is water specifically, whereas solvation, your solvent could be anything. Okay, and that more so applies to our other solutions which had things that were not water to be the solvent. Okay, so if we're talking about, let's say, metal alloys, okay, if we're talking about stainless steel, our solvent is not water. Okay, so when the solutes for making stainless steel are dissolving in the solute, we would call that solvation. Okay, now the process of dissolving, there's two major factors that are involved in the dissolving process. So one of them's going to be that the molecules tend to become more spread out, and the other factor is that energy is going to be either lost or gained. Okay. Now, when a substance is being dissolved, no new substance is being formed. So dissolving is not a chemical change, it's a physical change. All it's doing is taking your substance and just doing a phase change from one phase to a different phase. So if we're going back to that Kool-Aid powder and dissolving it in water, we're taking that Kool-Aid powder and turning it from a solid into an aqueous state. Okay, and energy is still going to be transferred because bonds are breaking and forming in the formation of a solution. Okay, so steps for dissolving. Step number 1, the forces between the particles in the solute break. So these are typically going to be your intermolecular forces. So that's like your London forces, dipole, and hydrogen bonding. Or it could be your ionic bonds. What determines which one of these it's going to be is the identity of your substance. So intermolecular forces, those are typically going to be for your molecular compounds, whereas ionic bonds, those belong to your ionic compounds. So London dispersion forces, also known as London forces. Dipole interactions. And then your hydrogen bonds. So this is mostly for your molecular compounds. Whereas ionic bonds, those are for your ionic compounds. All right, so the process in which the forces between particles are breaking, that's going to be endothermic. Okay, so endothermic, what does that mean? It means that energy is going into something. So essentially what this is saying is it takes or it requires energy to break either these intermolecular forces or these ionic bonds. Okay, and some intermolecular forces in the solvent break as well. So if we're talking about a solvent that's like water, there's hydrogen bonding happening between all the different water molecules. Okay, and when those break, that also requires energy, so it's an endothermic process. So you are going to have to know the difference between endothermic as well as exothermic processes. So endothermic just means that energy is required, whereas exothermic means that energy is being given off. Okay, so in step 3, the attraction between the particles of a solute and the particles of a solvent result in the forming of new solute to solvent bonds. So when bonds are being formed, it's exothermic, it gives off energy. But when bonds are being broken, that requires energy to do that. Okay, so it's kind of like for a rubber band. If you were going to break a rubber band, that would require energy from you in order to do it. Okay, now in this analogy, the rubber band is the forces between molecules or particles, I should say. So those could either be your intermolecular forces or your ionic bonds, something like that. Okay. So the overall energy change is going to be the sum of the above three processes. Okay, so the sum of the three processes being like forces between particles breaking, and forces between the solvent particles breaking, those are both being endothermic, and then the attraction between particles of solute with particles of solvent, which is an exothermic process. The overall energy change of those two endothermic processes with that last exothermic process is going to determine whether you have overall an exothermic process or an endothermic process. So if more energy is absorbed to break the bonds than the amount of energy released when the bonds are formed, overall change is going to be endothermic because there's a net negative amount of energy, okay, because more energy was required to break the bonds than is given off. But if more energy is released when the solvent bonds form than is required to dissolve the solvent, then overall energy change is going to be exothermic, okay? So to make this a little bit more relatable with endothermic versus exothermic, we can think about hot and cold packs. So for a hot pack, when you break it up to get the reaction going, obviously some energy needs to be put into breaking the bonds in the substances that's within the hot pack. Okay, so there is a bit of an endothermic process to that. However, there's a lot more energy given off by new bonds being formed within the energy, or not the energy pack, the hot pack. And you feel that because it gets hot. There's lots of energy being released. However, with a cold pack, okay, more energy is required to break the bonds of the substance that's within the cold pack than the energy that's released when new bonds formed. Okay, and as a result, we feel it as cold. So for a hot pack, more energy is released as new bonds are formed compared to the energy that's required to break bonds within the substances. And we're going to feel this as heat. Whereas for cold packs, more energy is required to break bonds compared to the energy released upon forming new bonds, we feel this as cold. Okay, because where the energy is coming from is from the surroundings. So basically, in order to properly break the bonds within the cold pack, it's drawing energy from the surroundings. So you could be part of the surroundings of this cold pack, and that's why you feel it as cold, because it's basically taking away energy from you in the form of heat in order to get the reaction to happen. Okay, so in terms of solubility, since that's a bit of a larger topic here, I'm going to be leaving that to the next video here.